In this video, we're going to be looking at optimization problems. Optimization problems have to do with finding the minimum or maximum value of some function over an interval. An example may be if you are looking at profit and you have a profit equation represented by the number of units you produce, and you get something that may look like this. If you're looking for the maximum profit on, say, this interval from A to B, we can see that the maximum profit would occur right here for this number of units being produced. Now, if we can create a function that represents this profit, we can use the techniques that we've learned in prior lessons, finding the first derivative of the function, setting it equal to 0 to find where the slope of the tangent line would equal 0, and then we could determine the maximum and minimum values. Another example may be if you have, let's say we have the area of some pen you're trying to create to hold some cattle as a function of the width of the pen. So if you have some function that represents the area versus the width of the pen, again, we create some function on an interval that represents this situation, and then we can take the first derivative of the function to find this maximum value, where it occurs. What should the width of the pen be to get our maximum area? So those are just a couple of examples of where we're using optimization. Now, this is used very frequently in other disciplines, as chemistry, economics, physics. A lot of other disciplines use this technique also, this optimization. So let's take a look at a couple of problems involving optimization. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? If I drew a diagram of this situation, we have this river, and we're going to build a fenced-in area along the river, so we do not need a fence along the river here. We do not need fencing there. Now, we do have 2,400 feet of fencing, and just to get a feel for this situation, what if we made the width of this 10 feet? This would be 10 feet. So we would have 2,380 feet left for this side. Because we have 2,400 feet of fence, we subtract off 20 feet for each, or for both sides, we'd have a total of 2,380 feet left. So if we made the width of our pen 10, well, the area then would be 10 times 2,380, so we'd have this much area. Now, if we changed this, let's say we changed the width of the pen to be, instead of 10, let's say we change it to 100, let's say. So we're going to make this a width of 100. Well, that would leave a length of 2,200. So if we have a width of if we have a width of 100, you can see that the area changes significantly. It jumps up to 220,000 square feet. So the area of this pen depends on the width of the pen. So we're going to try to come up with a function that represents the area as a function of the width, and then graph that function so we can try to find the maximum value of that function. So that's the idea behind a maximization or minimization or an optimization problem. So let's see how this works. What I like to do in these types of problems is just ask myself, what type of a problem is this? Are we trying to maximize something or minimize? So reading back over the problem, it says what are the dimensions of the field that has the largest area? So we're trying to maximize something. Then I just ask myself, what are we trying to maximize? And in this case, it's area of a rectangle. So we're trying to maximize the area of this rectangle. That is the function we're going to try to create, the area function. So to find the area of this rectangle, we don't know what the width would be to maximize the area. So let's just call the width x. So that's the width of our pen. So if that is x, this side would be x also. And if we wanted to say this is y, we could label that as y. And some of you may be thinking, well, I could label that in terms of x. That's okay if you wanted to do it that way. I'm just going to show it this way first, and then I might show how we could label that side in terms of x also. But let's just do it this way for now. So if we have the area, it's x times y. That would find the area of our rectangular pen. Now this is a function of two variables, x and y. I only want the area in terms of one of the variables, x. Now I typically will say this is my primary equation. This is the equation we're going to try to maximize, my primary equation. Now if I have two variables in my primary equation, I try to come up with a secondary equation that relates the two variables so I can solve one in terms of the other. Now in this problem, I'm concerned with these two variables. I have x and y. I want to get everything in terms of x, so I need to find a relationship that gives me an equation in terms of x and y. So if I look back at the problem, it tells me that I have 2,400 feet of fencing here. Well, that represents the perimeter. So the perimeter here of this pen would be x plus y plus x. That's the perimeter of the pen. So that would have to equal 2,400 feet. That's how much fencing I have to put around that perimeter. So if I combine my like terms, I get 2x plus y equals 2,400. And now I see I can solve for y here by subtracting 2x. And now over in my primary equation, I can replace y. I'm going to replace this y now with what it equals in terms of x. So we would have 2,400 minus 2x. Now thinking about what we have here, we have now the area in terms of the length of the side. Here's the function that represents that situation. So if we have some function that represents area as a function of the length of the side, how do we find a maximum or a minimum value on an interval? Well, let's see if we can define our interval. What would the minimum value of x be? Theoretically, we could say it is 0. That's the least it could be. What is the maximum value x could be? Well, since x represents the length of our sides here, if I split the entire fencing between the two, I could have 1,200 for each one of those widths. So theoretically, we could say up to 1,200. Now we realize that if we have 0 for the length or the width of this pen, we're not going to have any area. And if we have 1200, we're not going to have any area. But we're going to use the closed interval technique, and here's our closed interval, 0 to 1200. And we know that a maximum can occur at the endpoints, 0, 1200, or at a critical number within that interval. So to find the critical value, we find the derivative of our function. And let's multiply this through before we find the derivative, just to make it a little bit easier to work with. So if I multiplied the x through, I'd have 2400 times x minus 2x squared. Now if we find our derivative, we would get 2400 minus 4x. We would set our derivative equal to 0 and solve for x. So if we subtracted 2400 and then divided by -4, we would get x equals 600. Now that is our critical number. So up here, looking at our graph, we determined that our critical number here is 600. That's where we're saying we have a local maximum, we believe. Now the closed interval technique says you take your endpoints 0, 1200 and your critical number 600, plug it back into your equation to find where the maximum value occurs. But as we discussed, we know we would not have the largest area at our endpoints, so it must occur at our critical number. Now, did we answer the question? It says, what are the dimensions of the field? So we haven't answered the question. The dimensions then would be 600. Now we would need 600 for each side. So this would be 600. This would be 600. That's 1200. So we would have 1200 for this length. So we'd have a 600 by 1200 would be the dimensions that give us the largest area. And if we multiply those together, it looks like we would get 720,000 square feet. But the actual answer is the dimensions of the field. So that maximizes the area that we could create by putting a fenced-in corral alongside a river where we don't need fencing for that fourth site. So that's an optimization problem. We found the maximum value of our function area on that interval. Find the point on the parabola y squared equals 2x that is closest to the point 1, 4. Let's draw the equation, just a rough sketch of our relationship here, y squared equals 2x. It's not a function, but it is a sideways parabola, so it would look something like this. I'm just trying to get a feel for the problem. Find the point on the parabola, y squared equals 2x, that is closest to the point 1, 4. So if we have the point 1, 4, let's say out here, I'm trying to find the point on the parabola that is closest to this point out here at 1, 4. I know this would have to be perpendicular to the slope of the tangent line there. I know the closest point wouldn't be out here or back here. I know it has to be the one I've drawn in black. That's the shortest distance between the point and the graph. Okay, now I've got a feel for the problem. First question I'm going to ask myself is this a maximization or minimization problem? Now this says find the point that is closest, so I'm trying to minimize. The next question I ask myself is what am I trying to minimize? And that gives you the equation to write down, your primary equation. I'm trying to minimize the distance. Well, if I'm trying to minimize the distance between 2 points, I know the distance between 2 points is found by this formula, the distance formula. So that gives me the equation that I'm going to be using. That's my primary equation. Just by asking yourself those two questions. What am I doing in this problem, maximizing or minimizing? So I said minimizing something. Well, what am I trying to minimize? I'm minimizing the distance. That gives me my primary equation. Now, for one of the points, we have a given point at 1, 4. We could actually plug that in, let's say for y sub 1 and x sub 1. We can plug that point in to our distance equation. So if we plug that in, we would have our primary equation. Distance equals the square root. Now I don't have to subscript it because I only have one x, so x minus 1 squared plus y minus 4 squared. And there we have our distance equation. That's our primary equation. Notice we do have an x and a y. We have two variables here. So we're going to have to create a secondary equation that relates x and y together so we can solve for y in terms of x. Well, if we had a secondary equation in terms of x and y, we could replace that y. Looking back at the problem, we see that it gives us a relationship between x and y already. It says y squared equals 2x. So that is our secondary equation. We have y squared equals 2x. Now we could solve, for this particular problem, we could solve for x or y. I'm going to solve for x because if I solve for y, then I have plus or minus the square root of something. So I don't want to involve the plus or minus. So I'm just going to say y squared divided by 2 equals x. And then let's replace over here in our distance formula. We're going to replace this x. Oops, that didn't highlight very well. We're going to replace that x with this here. So if we replace x with y squared over 2 minus 1 squared plus y minus 4 squared. So we've just used this relationship to replace x in terms of y, and now we have this equation in terms of y only. Now we need to find the derivative of this equation. I think what we'll do is multiply this out first underneath and gather our like terms. So we would get y to the 4th over 4 minus, now when I take the next two terms, I'm just multiplying y squared over 2 minus 1 times y squared minus 2. I'm just multiplying this times this. I'm just doing that operation, squaring it. So we got y to the fourth over 4, and then we'd have minus 2 times y squared. So we would have this times this, and this times this. So we would have negative y squared over 2 minus y squared over 2, which gives us this. So we'd have minus y squared plus 1, and then we're going to square this binomial, y minus 4. We would get y squared minus 8y plus 16. If we gathered up our like terms now, we have, looks like we have something that will cancel here. We have our y squared, negative y squared, those cancel. So we would have the distance equals, we have y to the fourth over 4 minus 8y plus 17. So now we need to take the derivative. So if we take the derivative of this function, just recall, if we take the derivative of the square root of f of x, we know the derivative is 1 all over 2 times the square root of f of x times f prime of x. If we set this equal to 0, we only have to be concerned where is the numerator equal to 0. So d prime equals, now I'm going to be using this here, the derivative of the inside function would be, we bring down the 4, then subtract 1 from the exponent, so we'd have y cubed minus 8, there's the derivative of the inside function, all over our 2 times the square root of y to the fourth over 4 minus 8y plus 17. We're going to set our derivative equal to 0. If we set our derivative equal to 0, we're only concerned where the numerator equals 0. If you looked at the denominator, we do check for critical numbers when the denominator equals 0, but the denominator is not going to equal 0. So we're just going to check where y cubed minus 8 equals 0. If we subtract or add 8 to both sides, we get y cubed equals 8, so y equals the cube root of 8, which is 2. Now that gives us the y value, where this distance would be minimized. So we know the y value is 2. And if we go back to our secondary equation, we could find the x value. If we plugged in 2 for y, we'd have 2 squared. And then we could solve for x, which would give us x equals 2. Now this problem, I didn't check the endpoints because I knew that the endpoints wouldn't really make sense. If I shot this all the way out here to an endpoint, well, where can I stop? It's going all the way out to infinity. And here, if I tried to reason, well, this might be an endpoint right here at x equals 0, well, I can see from the diagram that's not going to give me a minimum distance. I know the minimum distance is going to occur at the critical number. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? Let's label a few things on this diagram. It says this should have a square base. So this distance, if we called this x, we know this distance here would be x also because it has to be a square base. And then I'm going to label the height of the box as h. Now looking at the problem again, I'm going to ask myself, what are we doing, maximizing or minimizing? What dimensions will produce a box with maximum volume? So I'm trying to maximize the volume. So that gives me the equation. My primary equation is going to come from maximizing the volume. Now, how do you find the volume of this box? It does say it's an open top box, so keep that in mind. So the volume of this box would be length times width times height, or x squared times h. So there's our primary equation. We have two variables, so I am going to try to find a secondary equation that relates x and h together so I can replace one in terms of the other. Looking back at the problem, we see that the surface area has, the surface area of the box is 108 square inches. To find the surface area, I would look at the surface of each one of these sides and the bottom and add them together. So the bottom of the box has a surface area of x squared. So that's the bottom of the box. This side here would have an area of xh. This would have an area of x times h, x times h, x times h. So we have 4 of those. So plus 4x times h. And since the surface area is 108 square inches, if we found the surface area of all the sides, it has to equal 108 square inches. So there we have found a secondary equation that relates x and h together. If we want to solve for x, if we want to solve for h, doesn't matter. Let's look at solving for, because in the very end we have to find the dimensions. We have to have h, we have to have x. So it doesn't matter which one of these we solve for. So if we solved for, let's say, we solve for h, we would subtract, I don't know where that came from, we would subtract x squared from both sides, and then we can divide by 4x, or I'll do it in 2 steps. So here we're dividing by x, and then if we divide by 4, so we have h in terms of x. If we simplified this a little bit, if we said 108 divided by 4x, that should be 27 over x minus, and we'd have x over 4. Now you could leave it as a common denominator, or you could change it like I did. Either way is fine. So here's our primary equation, x squared times h. And let's replace h with, now here's what h is equivalent to, either this one or the one below it. So let's plug that in, 108 minus x squared all over 4x. Now we have our primary equation in one variable. So if we simplify this a little bit before we find our derivative, we can reduce one of these x's. So we would have x times 108 minus x squared all over 4. So our volume would be 27x minus 1/4 x cubed. Now we can find our derivative. V prime is 27 minus 3/4 x squared. And when we set this equal to 0, now we're going to solve for x. So if we subtract 27 and then we're going to divide by a -3/4 or multiply by the reciprocal. So I'm looking at this saying, well, 27 divided by 3 is 9. 9 times 4 is 36. So it looks like we'll get 36 equals x squared. Now we don't need the negative value. Typically we say plus or minus, but we can't have a negative distance, so we get x equals 6. Now let's look at the endpoints. What would the endpoints represent? Here we're looking at the volume as a function of the length of one of the bases. So our independent variable x represents the length of the base. So again, theoretically we could have a 0 for the length, but we wouldn't have any volume, so that's not going to maximize the volume. Now the maximum that could be is if we think about the piece of metal or whatever it's made out of flattened out before we try to create a box from this. The total surface area here is 108, so that would mean this had to be the square root of 108. This would have to be the square root of 108. So that would give us the maximum width it could be. But if we make the sides the square root of 108, we don't have any height, so there's no volume again. So we can conclude that our critical number is going to be the maximum volume. At that critical number, which represents the length of the base, that will give us the maximum volume for this box. Now it says what dimensions will produce a box with a maximum volume. So the dimensions would be 6 by 6, which is 36, and then we would have to have the remaining dimension give us what we multiply by would have to be 108. And so if we have 36, and if we multiply that by 3, hopefully that will give us our 108. So we'd have a 6 by 6 by 3. That would give us the dimensions of the box here. That would give us a maximum volume. So there we've optimized the volume, found the maximum value for the volume of this container.